Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in wherever you are. Let your body sink into comfort, releasing whatever tensions the day has left behind. There's nowhere you need to be, nothing you need to accomplish. Just gentle exploration ahead. Where in the world are you right now? A quiet room where you can finally let your mind rest. A peaceful space where the day's noise has faded. Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of the most profound questions humans have ever contemplated. What's on the other side of the Big Bang? We'll discover that this seemingly straightforward question opens into deep mysteries about the nature of time, the beginning of existence, and whether before even makes sense when discussing the universe's origin. The answer might be nothing, or something quite surprising. Or the question itself might need reformulating. But don't worry, this isn't going to be an overwhelming journey through impossible abstractions or a dizzying plunge into conceptual paradoxes. Instead, we'll move slowly and thoughtfully through the possibilities, building understanding piece by piece, finding clarity where confusion seemed inevitable. By the end, I think you'll have a richer appreciation not just for what might have preceded our universe, but for why this question reveals something profound about time's nature. If you enjoy these calm explorations of cosmic origins and fundamental mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds, so settle in now. Let your shoulders drop, releasing tension you didn't know you were carrying. Take a slow, deep breath in, feeling your lungs expand and release it gently. Feel yourself sinking deeper into comfort with each exhale, and let's begin our slow drift through time's beginning, exploring what it means for something to come first and whether anything could precede everything. There's nowhere you need to be, no boundaries you must cross. Just listen, and let the mysteries unfold like time itself flowing from its origin. To understand what might be on the other side of the Big Bang, we first need to understand what the Big Bang actually is, according to our current best scientific model. The Big Bang is not an explosion in pre-existing space. This is perhaps the most common misconception, the image of a cosmic bomb detonating at some point in an empty void. Instead, the Big Bang represents the beginning of space and time themselves. It's the moment when the universe transitioned from an infinitely dense, infinitely hot state to the expanding cosmos we observe. Approximately 13.8 billion years ago, everything we can observe was compressed into an extraordinarily small region, much smaller than a single atom. At this moment, space itself began expanding. Not expanding into anything, but rather space itself growing, carrying matter and energy along with it. Temperature and density were unimaginably extreme. The universe was filled with intensely energetic radiation, so hot that even fundamental particles couldn't form stable structures. As space expanded, it cooled. This cooling allowed particles to form, then atoms, then eventually stars and galaxies across billions of years. This singularity isn't a place or a moment we can describe physically. It's a boundary where our theories fail, where the mathematics tells us it cannot be trusted. The singularity appears at time equals zero in our equations. Before this moment, standard Big Bang cosmology simply doesn't apply. This creates the question, is the singularity real? Or is it an artifact of using theories beyond their valid regime? Does time truly begin there, or is something else happening? General relativity is a classical theory. It doesn't incorporate quantum mechanics, which becomes essential at the extremely small scales present near the singularity. At the Planck scale, about 10 to the minus 35 meters and 10 to the minus 43 seconds, quantum effects dominate and classical descriptions fail. The Big Bang singularity occurs at or near this Planck regime. To understand what really happens, there requires quantum gravity, a theory we don't yet have complete. Without quantum gravity, we cannot definitively say what happens at the singularity. The standard Big Bang model is simply silent about this moment. This leaves open the profound question of what came before. Did time begin at the Big Bang, making before meaningless? Or did something exist before that our current theories cannot describe? Different theoretical approaches to quantum gravity suggest different answers. Some propose the singularity is resolved and replaced with a bounce from a previous phase. Others suggest time itself emerges from a timeless quantum state, making before a concept without meaning. Still others propose the universe tunneled from nothing quantum mechanically. The standard Big Bang model is extraordinarily successful at describing the universe's evolution from its earliest observable moments to the present, but it explicitly cannot address the very beginning itself. This is not a failure of observation, but a limitation of the theoretical framework. To go beyond this limitation requires new physics. Quantum cosmology attempts to apply quantum mechanics to the universe as a whole. Various proposals exist for what replaces the singularity or what exists on the other side of it. We'll explore these throughout this journey. For now, we establish that the standard Big Bang model gives us a timeline. At 13.8 billion years ago, something happened that we call the Big Bang. The universe emerged from an extremely hot, dense state and began expanding. But what that state was, how it arose, and whether anything preceded it remain open questions. These are not idle philosophical speculations, but genuine scientific questions at the frontier of cosmology and fundamental physics. The standard model takes us to a boundary, the singularity, where it admits its own incompleteness. What's on the other side of that boundary is tonight's exploration. The singularity at the Big Bang represents both a crisis and an opportunity for physics. A boundary where current understanding breaks down and new insights are required. In general relativity, a singularity is a point where space-time curvature becomes infinite. The mathematical description of space-time fails at such points. Black holes contain singularities at their centres. The Big Bang singularity is similar but represents the beginning of all space-time rather than a location within it. At the singularity, density becomes infinite. All the universe's mass energy is compressed into zero volume. Temperature becomes infinite as well. These infinities are problematic. Physics doesn't like infinities appearing in physical quantities. They usually signal that the theory is being pushed beyond its limits. When a theory predicts infinities, it's telling us it's incomplete. Something is missing from the description that would resolve the infinity into something finite. For black hole singularities, quantum gravity is expected to resolve the infinity into something physically sensible, perhaps a high density but finite state. Similarly, for the Big Bang singularity, quantum gravity should replace the infinite density point with something describable, though we don't yet know what. The singularity represents a breakdown not just of mathematical description, but of predictability. The future cannot be predicted from conditions at a singularity. This makes the singularity a boundary of physics in a deep sense. Beyond this boundary, our equations give no information. We're fundamentally unable to extrapolate further. Cosmologists distinguish between two types of singularities. Curvature singularities involve infinite space-time curvature, like the Big Bang and black hole centers. Coordinate singularities are artifacts of particular coordinate choices and can be removed by using different coordinates. These aren't real physical infinities. The Big Bang singularity appears to be a genuine curvature singularity. It cannot be removed by clever coordinate choices. It represents real physics going wrong. Penrose and Hawking proved singularity theorems in the 1960s, showing that singularities are generic in general relativity under reasonable conditions. If the universe is expanding and contains matter with normal properties, tracing backward in time inevitably leads to a singularity. It's not a special case, but a general prediction. This made cosmologists take singularities seriously as real features of the universe's history, not just mathematical artifacts. What happens at the Planck scale when quantum gravity effects dominate? We don't know precisely because we don't have a complete theory. String theory, loop quantum gravity, and other approaches make different predictions about Planck scale physics, and thus about singularity resolution. The singularity problem is thus both a fundamental limitation of current theory and a signpost pointing toward new physics. It tells us where general relativity stops being valid. It marks the boundary between what we can describe with current physics and what requires new understanding. In this sense, asking what's on the other side of the Big Bang is asking what lies beyond this theoretical boundary. What does quantum gravity reveal? The singularity is not an impenetrable wall, but a fog of ignorance. We know our theories fail there, but we don't yet know what correct description replaces them. Multiple theoretical proposals exist, each suggesting different answers to what happens at or before the singularity. We'll explore these possibilities systematically. But the key insight is that the singularity problem is not philosophical but physical. It's a real limitation demanding real solutions from physics. Understanding what's on the other side of the Big Bang requires resolving the singularity, understanding what quantum gravity says about the universe's origin. This is an active area of research. Theoretical physicists are working to develop quantum gravity theories that can address these questions. Observational cosmologists are looking for signatures in the cosmic microwave background or other data that might provide clues about Planck-scale physics. The singularity problem frames our inquiry. We seek to understand what happens when general relativity's description breaks down at the universe's beginning. One of the most fundamental questions about the Big Bang is whether time itself began at that moment, or whether time extends further back into a pre-Big Bang era. In everyday experience, time seems absolute and universal. It flows forward at a steady rate, independent of what's happening. But Einstein's relativity showed that time is relative, different for different observers. Time is not separate from space, but part of unified space-time. General relativity treats time as a coordinate, similar to spatial coordinates. Space-time is a four-dimensional structure where time is one dimension. If space-time itself began at the Big Bang, then time began there too. There would be no moments before because time didn't exist yet. This might seem strange or unsatisfying. How can time begin? Doesn't beginning imply a before when there was no time? Many physicists find this intellectually satisfying. It avoids infinite regress of causes. It provides a definite starting point without requiring explanation of before, but others find it unsatisfying. It seems to replace the question of origins with a statement that the question is meaningless. Moreover, quantum gravity theories might change this picture. If quantum effects resolve the singularity, time might not begin but continue through the Big Bang. In loop quantum gravity, for instance, the singularity is replaced by a quantum bounce. The universe contracts from a previous phase, reaches minimum size, then bounces into expansion. In this scenario, time continues through the bounce. There is a before, a contracting phase preceding the expanding phase we observe. String theory scenarios sometimes involve similar ideas. Higher dimensional branes might collide, creating our universe. Time would exist in the higher dimensional space before collision. Eternal inflation involves time extending infinitely into the past. Inflation has been occurring eternally, with our universe one bubble where inflation ended. These scenarios suggest time doesn't begin at the Big Bang but continues through it or past it. The Big Bang becomes a transition rather than absolute origin. The question of whether time has a beginning thus depends on which quantum gravity theory is correct, something we don't yet know. Different theories make different predictions. Observational tests might eventually distinguish them, but currently they remain competing hypotheses. Some theories treat time differently at the quantum level. Time might emerge from something more fundamental rather than being fundamental itself. In Wheeler-DeWitt quantum cosmology, the wave function of the universe is timeless. Time emerges as an approximate concept in certain regimes but isn't fundamental. If time is emergent, Asking about time's beginning is asking about when the emergent approximation becomes valid, not about fundamental reality. If time extends before the Big Bang, then prior states might have caused or evolved into the Big Bang, restoring a causal chain. The question of time's beginning is thus intimately connected to questions of causation, explanation, and the universe's ultimate origin. Current physics doesn't definitively answer whether time began at the Big Bang. Both possibilities remain open depending on correct quantum gravity theory. What we can say is that the question is scientifically meaningful and potentially answerable. It's not merely philosophical speculation, but a question about physical reality. Future developments in quantum gravity and cosmology might provide definitive answers, or might reveal that the question needs reformulating in unexpected ways. For now, we acknowledge the uncertainty. Time might have begun at the Big Bang, or it might extend further back. What's on the other side depends partly on this answer. Quantum mechanics fundamentally changes how we think about the universe's origin, introducing uncertainty, probabilistic behavior, and the possibility of creation from nothing. At macroscopic scales, quantum effects are negligible. Objects have definite positions and properties. Cause and effect operate deterministically. But at microscopic scales, quantum mechanics dominates. Particles exist in superpositions of states. Properties are probabilistic until measured. The uncertainty principle limits how precisely we can know complementary properties like position and momentum simultaneously. This uncertainty has profound implications for the universe's origin. At the Planck scale, relevant near the Big Bang, quantum uncertainty becomes cosmologically significant. In quantum mechanics, energy can fluctuate temporarily from nothing due to uncertainty. Virtual particle pairs constantly appear and disappear in vacuum. These fluctuations are real. Observable through effects like the Casimir force, the vacuum seethes with quantum activity even when appearing empty. Could the entire universe be an enormous quantum fluctuation? Could it have emerged from nothing through quantum uncertainty? This idea faces immediate challenges. Energy conservation appears to forbid creating something from nothing, even temporarily. But the universe's total energy might be zero. Positive mass energy is balanced by negative gravitational potential energy. Hartley and Hawking proposed that the universe has no initial boundary in imaginary time. The Big Bang singularity is smoothed out in a four-dimensional Euclidean space. In this proposal, time becomes space-like near the origin. There's no sharp beginning but a smooth geometric structure without boundaries. Asking what came before the Big Bang is like asking what's south of the South Pole. The question presumes structure that doesn't exist. The universe simply is, described by a wave function that includes all of space-time without needing an external beginning point. This is elegant but strange. It requires accepting imaginary time as physically meaningful and understanding how real time emerges from it. An alternative quantum approach is Vilenkin's tunneling proposal. The universe tunnels from nothing into existence quantum mechanically. In quantum mechanics, particles can tunnel through barriers that classical physics forbids. The universe might tunnel from non-existence to existence. This requires defining what nothing means quantum mechanically. It's not philosophical absolute nothing, but a state without classical space-time. The tunneling occurs in a space of possible universe geometries. The probability of tunneling into different geometries can be calculated quantum mechanically. Both Hartle-Hawking and Vilenkin proposals attempt to explain the universe's origin without requiring anything before or outside it. They treat the Big Bang as a quantum event, probabilistic and subject to quantum laws rather than classical determinism. Critics question whether quantum mechanics can be applied to the universe as a whole. Quantum mechanics normally involves systems and observers. For the universe, there's no outside observer. The wave function describes everything. This might require rethinking quantum mechanics foundations. Another quantum approach involves pre-Big Bang scenarios, where quantum effects prevent the singularity, and allow continuation from a previous phase. Loop quantum cosmology, based on loop quantum gravity, predicts quantum bounces. The universe contracts to about 10 to the minus 35 meters, then bounces into expansion. Quantum repulsive effects arise from loop quantum gravity's discrete space structure, preventing infinite compression. In this scenario, the Big Bang is a bounce from a previous contracting phase. Quantum mechanics connects our expanding universe to a predecessor. What existed before, another universe, possibly similar to ours, that was contracting. Before that, perhaps another cycle. Extending indefinitely into the past. The quantum origin approaches share the insight that classical general relativity's singularity is replaced by quantum processes when properly treated. Whether this results in a universe from nothing, a smooth beginning without before, or a bounce from a previous phase depends on theoretical details. All these approaches remain speculative. We lack experimental tests of quantum gravity that would confirm or refute these scenarios. But they illustrate how quantum mechanics transforms the origin question. Classical certainties dissolve into quantum probabilities and uncertainties. What's on the other side of the Big Bang might be quantum indeterminacy rather than definite prior states. The origin might be probabilistic, not determined. This quantum perspective suggests the universe's beginning is not a moment we can point to definitively, but a region where quantum effects dominate. In that quantum region, classical concepts like before and after blur into superpositions and probabilities, requiring new ways of thinking about origins. One ancient and intuitively appealing answer to what's on the other side of the Big Bang is another universe, part of an eternal cycle of cosmic death and rebirth. The idea of cyclic time appears in many ancient traditions. Hindu cosmology describes infinite cycles of creation and destruction spanning vast timescales. Ancient Greek philosophers, including the Stoics, proposed eternal recurrence, with the universe periodically returning to the same state and repeating. Modern physics has entertained similar ideas, though with crucial differences from ancient conceptions. Eventually, if entropy keeps increasing, the universe might not recollapse but expand forever. This makes the cyclic model unstable over infinite time. Some cyclic proposals address this by having entropy reset somehow at each bounce. But the mechanism is unclear and potentially violates thermodynamics. Modern cyclic models often involve extra dimensions or modifications to gravity, rather than simple general relativity. The ekpyrotic scenario, based on string theory, proposes that our Big Bang resulted from collision of higher dimensional branes. Two three-dimensional branes moving through extra dimensions periodically collide. Each collision creates a Big Bang in each brane. Between collisions, the branes separate, creating an expanding phase. Then attraction brings them together again for another collision. This creates a cycle driven by brane dynamics in higher dimensional space. The cycles can continue indefinitely without entropy problems. What's on the other side of the Big Bang in ekpyrotic scenarios is the previous brane collision and the intervening expansion phase. These models make specific predictions about the pattern of density fluctuations in the cosmic microwave background, potentially distinguishing them from inflation. Observations so far favour inflationary predictions over ekpyrotic ones, but the tests are not yet definitive enough to rule out cyclic models. Roger Penrose's conformal cyclic cosmology takes a different approach. Each cycle ends in heat death. Infinite dilution rather than contraction. But Penrose argues this infinitely dilute end state is mathematically equivalent to a new Big Bang through conformal transformation. The massless particles remaining after everything else has decayed or left the horizon lose the ability to measure scale. Large becomes indistinguishable from small. This scale invariant state can be conformally mapped to a new Big Bang, starting the next aeon with low entropy. The cycles don't involve contraction and bounce, but rather transformation of infinite expansion into new beginning. Penrose claims to see evidence of previous aeons in circular patterns in the cosmic microwave background, from colliding black holes in the previous aeon. Other researchers dispute these claimed detections. The patterns might be statistical artifacts rather than genuine signals from previous cycles. Cyclic cosmology faces the challenge of explaining why this particular cycle looks the way it does if infinite cycles preceded it. By ergodic principles, shouldn't earlier cycles have explored all possibilities? Why aren't we in a typical late-stage cycle with maximum entropy? This is similar to the Boltzmann brane problem. In eternal time, random fluctuations should dominate over ordered states like our universe. Cyclic models must explain anthropic selection. We observe a habitable cycle because we can only exist in such cycles, even if they're rare. Despite challenges, cyclic cosmology remains an active research area. It offers intuitive appeal and potential solutions to cosmological puzzles. If some version is correct, what's on the other side of the Big Bang is another universe, similar or different, that preceded ours in an eternal sequence. Time extends infinitely into the past through previous cycles. The Big Bang is a transition point, but not the beginning of everything. This dramatically changes the origin question. Instead of asking about ultimate beginning, we ask about the mechanism of bounces and the nature of cycles. The philosophical implications are profound. An eternal cyclic universe needs no creation, no first cause, no external explanation. It simply is, eternal and self-sustaining, with our cycle one moment in infinite temporal extent. Whether this is correct depends on testing theoretical predictions against observations and resolving theoretical problems like entropy increase. For now, it remains one possibility among several for what might lie on the other side of the Big Bang, an ancient idea reimagined through modern physics. Loop quantum gravity offers one of the most developed approaches to quantum gravity, with specific predictions about what happens at the Big Bang singularity. Loop quantum gravity treats space-time as fundamentally discrete at the Planck scale rather than continuous. Space is woven from quantum threads called spin networks, tiny loops of quantized geometry connected in a network. These loops have discrete sizes, about 1 Planck length, roughly 10 to the minus 35 meters. Space cannot be divided smaller than this fundamental quantum. This discreteness has profound implications for cosmology. If space has minimum size, the universe cannot contract to zero volume. Loop quantum cosmology applies loop quantum gravity principles to the early universe, studying how the Big Bang singularity is resolved. The key finding is quantum bounce. As the universe contracts, quantum effects become strong at roughly 1/10,000th of the Planck density. The spectrum of density fluctuations in our universe might carry signatures from the previous universe's late stages. These predictions could potentially be tested through precise measurements of the cosmic microwave background and large-scale structure. Loop quantum cosmology resolves the singularity problem elegantly. The infinite density predicted by classical general relativity is replaced by high but finite maximum density. The theory is background independent, meaning it doesn't assume a pre-existing spacetime structure. Spacetime emerges from quantum spin networks. This is considered essential for a true quantum gravity theory. General relativity is also background independent, treating geometry as dynamic. Loop quantum gravity preserves this key feature while quantizing geometry itself. The bounce occurs when the scale factor reaches minimum, corresponding to maximum energy density allowed by quantum effects. Numerical simulations show the bounce is robust. Different initial conditions lead to similar behavior. The bounce is generic, not requiring fine-tuning. After the bounce, the universe expands rapidly. This rapid expansion naturally mimics inflation's effects, potentially explaining why the universe appears flat and homogeneous. If this is correct, cosmic inflation might not be necessary. The quantum bounce provides alternative explanation for observed large-scale properties. However, loop quantum cosmology faces challenges. The theory is not yet complete. Many technical questions remain about its mathematical consistency. the connection between loop quantum gravity's fundamental variables and observable spacetime geometry isn't fully understood. Critics also question whether quantum gravity effects can have such dramatic cosmological consequences. The Planck scale is extraordinarily tiny. Can dynamics at this scale really affect the entire universe's behaviour? Loop quantum cosmology says yes, through the cumulative effect of quantum discreteness. Another question is whether the previous universe's details significantly affect ours. If the bounce erases most information, the previous universe becomes largely irrelevant. But if substantial information transfers through the bounce, our universe's properties depend on previous conditions, pushing the origin question further back. In cyclic loop quantum cosmology, bounces might continue indefinitely. Each expansion phase eventually contracts due to some mechanism, bouncing again. This creates eternal cycling similar to classical cyclic models, but with quantum bounces replacing singularities. The entropy problem remains. Even with bounces, thermodynamics pushes toward increasing entropy. Over infinite cycles, entropy would keep growing. Either entropy resets somehow at bounces, or the cyclic chain isn't truly eternal, but began at some point with low entropy. These issues remain active research topics. Loop quantum cosmology provides concrete framework for addressing them, but definitive answers await further development. For our question, loop quantum cosmology offers clear answer. On the other side of the Big Bang is a previous universe that contracted and bounced. That universe might be similar to ours or quite different depending on how much information passes through the bounce. If cycles continue eternally backward, there might be no ultimate origin, just eternal sequence of bounces extending infinitely into the past. If cycles began at some point, that beginning requires explanation, perhaps from quantum creation or other mechanisms. Loop quantum cosmology thus transforms the Big Bang from absolute beginning into a transition point in potentially infinite cosmic evolution. String theory, another leading approach to quantum gravity, suggests different possibilities for what might precede the Big Bang. String theory proposes fundamental constituents are one-dimensional strings rather than point particles. Different vibration modes correspond to different particles. For mathematical consistency, string theory requires extra spatial dimensions beyond the 3 we experience. Most versions require 9 or 10 spatial dimensions. 6 or 7 of these extra dimensions must be compactified, curled up to tiny sizes we don't directly perceive. This scenario can be cyclic if the branes separate after collision, then attraction brings them together for subsequent collisions. Alternatively, the collision might be a one-time event, with branes separating permanently afterward. Future would differ from cyclic predictions. String cosmology also explores pre-Big Bang scenarios where our universe emerged from different string vacuum state. The universe might have tunneled from false vacuum to true vacuum, releasing energy that drove expansion we call the Big Bang. Or the universe might have started in a perturbative regime of string theory, where strings interact weakly, then transitioned to our current strong coupling regime. String gas cosmology proposes the early universe was filled with gas of strings wrapping around compactified dimensions. As the universe cooled, strings unwound from some dimensions, allowing those dimensions to expand while others remained compact. This creates our 4 large dimensions from an initially more symmetric, higher dimensional state. What preceded the Big Bang in string gas cosmology is a hot, dense state with different dimensional structure, all dimensions similar in size. The transition to our current dimensional structure defines the Big Bang, but string gas existed before with different properties. Duality symmetries in string theory offer another perspective. Different string theory descriptions can be equivalent, related by dualities. Some dualities relate small and large scales. A universe contracting in one description is equivalent to expansion in dual description. This raises possibility that Big Crunch in contracting universe is dual to Big Bang in expanding universe. They're the same physics from different perspectives. If true, What's on the other side of the Big Bang is our own universe's future end state, viewed through duality transformation. This is highly speculative, but illustrates string theory's conceptual richness and potential for surprising connections. String cosmology faces significant challenges. String theory is not yet complete. We don't have unique predictive framework, but rather a landscape of possibilities. The landscape contains perhaps 10 to the 500th distinct vacuum states. Without principle selecting among them, predictions become difficult. Different vacua suggest different pre-Big Bang scenarios. The answer to our question might vary across the landscape. Anthropic reasoning might constrain which vacua are relevant. We observe vacua compatible with observers, which might be rare in landscape. The answers range from brane collisions in higher dimensions, to vacuum transitions, to dimensional structure changes, to duality-related connections to the future. All involve pre-Big Bang states that differ significantly from our current universe, but are described by string theory's extended framework. Time generally continues through the Big Bang transition in string scenarios. The Big Bang is a dramatic event, but not an absolute beginning of time. Whether time extends infinitely into the past or began at some point depends on specific string cosmology details and remains unclear. String theory thus provides rich possibilities but not yet definitive answers. Further theoretical development and observational tests are needed. The potential connections between string theory's mathematical structure and pre-Big Bang cosmology remain exciting frontier of theoretical physics. Stephen Hawking and James Hartle proposed one of the most famous attempts to address what came before the Big Bang through quantum cosmology. Their approach treats the universe's wave function, the quantum description of all possible universe configurations. In quantum mechanics, particles have wave functions describing probability amplitudes for different states. The universe itself has analogous wave function. The Wheeler-DeWitt equation governs the universe's wave function, though solving it requires major approximations given complexity. Hartle and Hawking proposed a specific boundary condition for the universe's wave function, determining its form uniquely. Their proposal uses Feynman's path integral formulation of quantum mechanics. Probability amplitudes are calculated by summing over all possible histories. The quantum to classical transition occurs through decoherence as the universe grows and classical behaviour emerges from quantum substrate. The no-boundary proposal predicts a universe that's nearly flat and homogeneous, matching observations. It naturally explains these properties. It also predicts specific spectrum of primordial density fluctuations, similar to predictions from inflation but derived from quantum gravity principles. The proposal has been immensely influential, inspiring much research in quantum cosmology and providing concrete framework for calculations. But it also faces significant challenges and criticisms from technical and conceptual perspectives. One issue is interpretation of imaginary time. What does it mean physically? Is it real or just mathematical trick? Hawking argued imaginary time is as real time. The Euclidean geometry is the fundamental description, with Lorentzian space-time emerging. Critics question whether this makes physical sense. Can time really become space-like? How does the transition to real time occur? The proposal requires analytical continuation from Euclidean to Lorentzian signature. This mathematical procedure is well defined, but physical meaning is debated. Another challenge is the measure problem. The path integral sums over infinite geometries. How do you weigh them properly? Different weighting choices give different predictions. The prescription for proper measure remains controversial. Some calculations suggest the no-boundary proposal predicts universes very different from ours, more likely than universes like ours. If true, this would be problematic. The proposal should explain why our universe is typical or at least probable, not extremely atypical. Recent work has revised some calculations, suggesting more favourable predictions, but debate continues. The proposal also requires quantum gravity to be well defined, which remains uncertain. String theory or loop quantum gravity might modify predictions. Despite challenges, the no-boundary proposal represents a landmark attempt to apply quantum mechanics to cosmology's origin question. It offers specific answer to what's on the other side of the Big Bang. Smooth, boundaryless geometry in imaginary time, not prior classical universe. This dissolves the question rather than answering it in conventional terms. There's no other side because there's no boundary to have another side of. Whether this interpretation is correct depends on whether imaginary time description is physically fundamental or merely mathematical convenience. It also depends on whether quantum cosmology of this type correctly describes the actual universe's quantum state. These remain open questions at the frontier of theoretical physics, unlikely to be resolved without major breakthroughs in quantum gravity. For now, the Hartle-Hawking proposal stands as one bold attempt to address cosmic origins through quantum principles, offering possibility that time itself is emergent. Alexander Vilenkin proposed that the universe might have tunneled into existence from literally nothing through quantum mechanical processes. Quantum tunneling allows particles to pass through barriers forbidden by classical physics. A particle can appear on the other side of a barrier even without sufficient energy to go over it. This occurs through quantum uncertainty. The particle's position becomes uncertain enough that it has non-zero probability of being beyond the barrier. Tunneling is experimentally verified in many contexts. Radioactive decay, tunnel diodes, and quantum computing all rely on tunneling. The calculation involves integrating over Euclidean geometries, connecting the initial nothing state to various possible classical universes. Different universe parameters have different tunneling probabilities. Smaller cosmological constants and masses generally have higher tunneling probability. Smooths out inhomogeneities and drives the universe toward flatness, explaining why we observe these properties. After inflation, standard Big Bang evolution proceeds. The hot, dense state we call the Big Bang is the aftermath of tunneling and inflation. What's on the other side of the Big Bang in Vilenkin's scenario is literally nothing. No space, no time, no matter, no energy. The universe didn't come from a previous universe or pre-existing state. It tunneled into existence quantum mechanically from zero size. This is creation ex nihilo, from nothing, but through natural quantum process rather than supernatural intervention. The appeal is that it requires no prior conditions, no external cause, no infinite regression. The universe is self-creating through quantum laws. But significant philosophical and physical questions arise. If nothing existed, how could quantum laws exist to govern tunneling? Quantum mechanics seems to require framework for its formulation. Laws, probabilities, Hilbert spaces. Can these exist in nothing? Vilenkin argues that mathematical laws don't require physical substrate. They're abstract structures that simply are independently of physical existence. If quantum mechanics is a mathematical structure, it exists necessarily, whether or not anything physical exists. The universe tunneling into existence is then inevitable, given quantum mechanics' existence, which is necessary as mathematical truth. Critics question whether this makes sense. Can mathematics exist without minds to conceive it? Is mathematics discovered or invented? These are deep questions in philosophy of mathematics, with no consensus answers. Another challenge is defining probability for universe creation. Probability normally refers to repeated trials or ensembles, but universe creation presumably occurred once. What does it mean to assign probability to unique event? Vilenkin uses probability as measure in space of possible universes. More probable universes occupy larger measure. This requires specific calculation of gravitational energy, which is subtle in general relativity. Different calculation methods give different results. In asymptotically flat spacetimes, total energy is well defined and can be zero. But for closed universes, the definition is more problematic. Vilenkin's proposal also faces technical challenges in properly defining the quantum state of nothing and the tunneling amplitude. The mathematics involves complex geometries and requires careful treatment to avoid infinities and ambiguities. Despite challenges, quantum tunneling from nothing represents serious scientific attempt to address ultimate origin without invoking anything prior. If correct, it provides stark answer to our question. On the other side of the Big Bang is nothing. The universe emerged from absence itself. This might seem unsatisfying, replacing mystery with deeper mystery of how quantum processes can create from nothing. But it represents progress in that it provides specific mechanism, even if that mechanism raises new questions about quantum mechanics' nature. The proposal connects to broader questions about why there is something rather than nothing, perhaps the deepest question philosophy can ask. Vilenkin's answer is that quantum mechanics makes something inevitable. Nothing is unstable quantum mechanically. Universes must form. Whether this is true depends on quantum cosmology's validity and correct interpretation of quantum mechanics applied to the whole universe. Some approaches to quantum gravity suggest time itself is not fundamental, but emerges from more basic timeless structures. If time emerges, asking what came before the Big Bang might be asking wrong question. The fundamental description might not involve time at all. The Wheeler-DeWitt equation of quantum cosmology contains no explicit time variable. It relates different configurations of the universe but doesn't say one comes before another. This perspective is philosophically radical. We experience time so fundamentally that imagining reality without time seems impossible. Yet quantum gravity hints that time might be approximate, valid only in certain regimes, not present in reality's deepest description. Julian Barber has developed this perspective extensively. He argues that time is illusion created by correlations between different parts of the universe. The universe is fundamentally a space of possible configurations, called configuration space, or, in Barber's terminology, Platonia. Each point in Platonia represents one possible arrangement of matter in space. The universe's quantum state is superposition over all configurations. These ideas connect to relational approaches to quantum mechanics. Perhaps quantum mechanics fundamentally describes correlations, not evolution. The universe's wave function specifies which configurations are correlated with which others. Our experience of time comes from navigating these correlations. Carlo Rovelli has explored similar ideas in context of loop quantum gravity, where time is treated as emergent from quantum gravitational processes. At Planck scale, time might not exist as fundamental parameter. Only relationships between different quantum variables exist. Time emerges as useful approximate concept when describing large-scale semi-classical systems where many degrees of freedom average out. These emergent time scenarios dramatically reconceptualize the origin question. If time emerges, the universe doesn't begin in time, but simply is timelessly. The Big Bang is transition in emergent temporal description, but not beginning of fundamental reality, which has no temporal structure to begin or end. This might resolve many paradoxes about origins. If there's no fundamental time, questions about what came before dissolve. Causation also becomes different. Without fundamental time, cause and effect are emergent notions describing correlations, not fundamental temporal relations. The universe doesn't need cause because causation requires time, and time isn't fundamental. The universe simply exists with certain correlation structure. Critics argue this trades one mystery for another. If time is emergent, what makes it emerge? Why do we experience temporal flow so convincingly? The emergence of time from timeless substrate might be as mysterious as creation of universe from nothing. We've shifted the mystery, not eliminated it. Moreover, physics is formulated in terms of time evolution. Rewriting all physics in timeless framework is enormously challenging, perhaps impossible. Can we really do quantum mechanics without time? Can we describe observations and measurements without temporal ordering? These are active research questions. Some progress has been made, but complete timeless reformulation of physics remains distant goal. For our question about what's on the other side of the Big Bang, emergent time scenarios suggest the question presupposes incorrect framework. There is no other side in time because time isn't fundamental. The Big Bang is feature in timeless quantum reality, not temporal boundary. This is satisfying to some, frustrating to others. It answers the question by suggesting the question misunderstands time's nature. Whether emergent time is correct depends on quantum gravity's correct formulation, which we don't yet have definitively. But it represents fascinating possibility that fundamental reality might be stranger than we imagine, lacking even the temporal structure we take as given. The cosmic microwave background provides our earliest observational view of the universe, offering potential clues about what preceded the Big Bang. The CMB is radiation from about 380,000 years after the Big Bang, when the universe became transparent to light. This is far after any quantum gravity effects at the Planck scale, which occurred at about 10 to the minus 43 seconds. Yet the CMB carries information about conditions at those earliest moments through the pattern of density fluctuations it reveals. The temperature variations in the CMB, about 1 part in 100,000, represent density variations in the early universe. These variations were seeded even earlier, during the universe's first moments, possibly during an inflationary period. Different theories about what preceded the Big Bang make different predictions about these primordial fluctuations. Standard inflation predicts an almost scale-invariant spectrum of fluctuations, meaning similar amplitudes at all scales with slight preference for larger scales. This prediction matches observations remarkably well. The CMB power spectrum follows the predicted pattern with extraordinary precision. Primordial gravitational waves would create a specific polarization pattern in the CMB called B-mode polarization. Different theories predict different amplitudes for these gravitational waves. Detecting them would provide crucial information about earliest moments. Standard inflation driven by a simple scalar field predicts detectable B-mode polarization, though the amplitude depends on the inflaton potential. Some cyclic models and bouncing cosmologies predict smaller or negligible primordial gravitational waves, providing potential way to distinguish them. The BISEP 2 experiment in 2014 announced detection of B-mode polarization, briefly causing excitement that inflation was confirmed. But subsequent analysis showed the signal was likely from dust in our galaxy, rather than primordial gravitational waves. Searches continue with improving sensitivity. Future experiments might detect primordial gravitational waves if they exist at observable levels. The non-detection so far constrains inflation models, ruling out those predicting large gravitational wave amplitudes. It also remains consistent with some bouncing cosmologies that predict very small primordial gravitational waves. Another CMB signature involves non-Gaussianity, deviations from pure Gaussian random distribution of fluctuations. Standard inflation predicts fluctuations are almost perfectly Gaussian. Alternative scenarios might produce more non-Gaussianity. Observations show fluctuations are consistent with Gaussianity within measurement precision, again favouring standard inflation. But subtle non-Gaussianity below current detection thresholds could exist, potentially revealing information about pre-inflation or pre-bounce physics. The scale dependence of the spectral index, how fluctuation amplitude varies with scale, also carries information about earliest moments. Measurements show slight scale dependence consistent with simple inflation models. More complex dependence might suggest alternative scenarios. Some ekpyrotic models predict blue spectrum at small scales rather than red spectrum inflation predicts. Observations favour red, challenging ekpyrotic models. However, theoretical developments might modify ekpyrotic predictions, so they're not definitively ruled out. These observations might find evidence for bounces, cycles, or other pre-Big Bang physics encoded in the universe's earliest observable light. Or they might further confirm standard inflation, ruling out alternatives and suggesting quantum origin or smooth no-boundary beginning. For now, the CMB provides our best observational window into the universe's earliest moments, though interpreting it requires theoretical frameworks. What it tells us about what's on the other side of the Big Bang is indirect, filtered through 13.8 billion years of evolution. But careful analysis of its patterns might yet reveal secrets of cosmic origins, distinguishing between competing visions of what came before. The distribution of galaxies across billions of light-years provides complementary information to the CMB about the universe's earliest moments and potential pre-Big Bang physics. Large-scale structure grew from tiny density variations present in the early universe. Denser regions attracted more matter gravitationally, growing into galaxies and clusters. The statistical properties of galaxy distributions today reflect the pattern of primordial fluctuations that seeded structure formation. By mapping how galaxies cluster at different scales, astronomers reconstruct the primordial fluctuation spectrum independently from the CMB. The Sloan Digital Sky Survey and subsequent surveys have mapped millions of galaxies, revealing the cosmic web of filaments, sheets, and voids. This structure's statistical properties match predictions from CMB-measured primordial fluctuations evolved forward through gravitational growth. The consistency between CMB and large-scale structure observations strongly validates the standard cosmological model, but subtle deviations might reveal physics beyond the standard model, potentially including signatures of pre-Big Bang conditions. Baryon acoustic oscillations, regular patterns in galaxy clustering from sound waves in the early universe, provide a standard ruler for cosmology. These oscillations peaked at a characteristic scale of about 500 million light-years. Measuring this scale tests cosmological models. BAO measurements are consistent with the CMB-derived cosmological parameters, providing independent confirmation. Alternative scenarios predicting different primordial fluctuation patterns would produce different BAO features, though differences might be subtle. The growth rate of structure over cosmic time also tests cosmological models. How quickly gravitational clustering proceeds depends on matter content and expansion history. If there was a bounce or cyclic transition, the growth rate might differ from standard predictions due to altered initial conditions or modified gravity. Observations of galaxy clustering at different redshifts measure this growth rate. So far, results are consistent with standard cosmology and general relativity. But precision is improving. Future surveys will measure growth more precisely, potentially detecting small deviations. Comparing these simulations to observations tests whether standard cosmology plus known astrophysics explains everything, or if anomalies remain. So far, observations match simulations reasonably well, though some tensions exist, like the missing satellites problem and cusp core issue. These problems might indicate missing astrophysics, or possibly hint at modified cosmology, though most researchers favour astrophysical solutions. Another probe involves the integrated Sachs-Wolf effect, where CMB photons gain or lose energy, passing through evolving gravitational potentials. The ISW effect creates correlations between CMB temperature and galaxy positions. Measuring these correlations tests dark energy properties and expansion history. Observations detect the ISW effect at expected levels, confirming the standard model. Deviations might suggest unusual expansion history from pre-Big Bang physics. Weak gravitational lensing, the subtle distortion of galaxy shapes by intervening matter, provides another probe of structure and expansion history. Lensing directly measures matter distribution, including dark matter. It's sensitive to growth rate and geometry in ways complementary to clustering. Lensing surveys find results consistent with CMB and other observations, again supporting standard cosmology. Tensions exist between some lensing measurements and CMB predictions, particularly for the amplitude of matter clustering. Whether these tensions represent systematic errors, new physics, or statistical fluctuations remains unclear. More precise measurements are needed. If tensions persist and strengthen, they might hint at modified physics, possibly connected to future precision measurements, might distinguish these scenarios through subtle features in clustering statistics or growth rates. Large-scale structure provides crucial observational constraints on any theory about the Big Bang and what preceded it. Whatever happened before must be compatible with the observed pattern of structure, a strong requirement that many speculative scenarios fail to meet. Gravitational waves provide a new window on the universe, potentially offering unique information about the earliest moments after or even before the Big Bang. Gravitational waves are ripples in space-time itself, travelling at light speed and passing through matter almost unimpeded. They're produced by accelerating masses, particularly dramatic events like black hole mergers or neutron-star collisions. The LIGO and Virgo detectors first observed gravitational waves in 2015 from merging black holes, opening gravitational wave astronomy. These detections observe relatively recent cosmic events, but gravitational waves from the early universe might also exist, creating a primordial background. Just as the CMB is background of photons from 380,000 years after the Big Bang, primordial gravitational waves would be background from much earlier. Gravitational waves can propagate from the universe's first moments because they interact so weakly with matter. No gravitational opacity exists. If produced during inflation, gravitational waves from within 10 to the minus 30 seconds after the Big Bang could reach us today. These waves would carry information about inflation's energy scale and dynamics, revealing physics at energies far beyond particle accelerator reach. Different models of inflation predict different amplitudes of primordial gravitational waves. High-energy inflation produces strong gravitational wave background. Detecting this background would confirm inflation occurred and measure its energy scale, crucial information about earliest moments. The waves would also create B-mode polarization patterns in the CMB, as mentioned earlier. This provides one detection method. But gravitational wave detectors themselves might eventually observe the primordial background directly, complementing CMB observations. Current detectors like LIGO are not sensitive to primordial gravitational waves, which have very low frequencies and tiny amplitudes. Future space-based detectors like LISA, launching in the 2030s, will observe lower frequency gravitational waves. LISA might detect gravitational waves from cosmic strings or phase transitions in the early universe, if these occurred. But primordial inflationary gravitational waves likely require even more sensitive detectors or pulsar timing arrays for direct detection. Pulsar timing arrays monitor millisecond pulses, looking for correlated timing variations from passing gravitational waves. They're sensitive to nanohertz frequency gravitational waves, complementary to LIGO's 100 Hz range and LISA's millihertz range. Recent results from pulsar timing arrays show hints of a gravitational wave background, though its origin isn't yet confirmed. If this background is primordial, it would be extraordinary discovery revealing earliest moment physics. More likely it's from supermassive black hole mergers, but future observations will determine the background's properties, potentially distinguishing primordial from astrophysical sources. Pre-Big Bang scenarios might produce distinctive gravitational wave signatures. A bounce from loop quantum cosmology could generate characteristic spectrum. The bounce involves rapid dynamics at Planck scale, potentially producing gravitational waves with specific frequency dependence. Cyclic models also predict gravitational waves from the bounce or brane collision, with spectra differing from standard inflation predictions. Detecting these signatures would provide smoking gun evidence for pre-Big Bang physics, confirming that something preceded our expansion phase. The absence of primordial gravitational waves would constrain inflation models and some alternative scenarios. Not all models produce observable waves. Gravitational wave observations thus provide crucial tests of early universe theories, complementary to electromagnetic observations. They probe physics inaccessible to particle accelerators or other experiments, making cosmology a laboratory for fundamental physics. The challenge is sensitivity. primordial gravitational waves are extraordinarily weak after 13.8 billion years of cosmic expansion. Detecting them requires instruments at the edge of technical possibility, carefully controlling noise and systematics. The payoff would be profound. Direct observation of the universe's first moments through gravitational radiation would revolutionize cosmology. It would answer fundamental questions about inflation, quantum gravity, and what preceded the Big Bang with observational data rather than theoretical speculation. Current and planned detectors are unlikely to reach required sensitivity for definitive detection, unless primordial amplitude is higher than most predictions. But technological advances continue. Detectors decades from now might achieve sensitivity beyond current imagination. Meanwhile, indirect detection through CMB modes remains possibility if inflationary gravitational waves have high enough amplitude. For our question about what's on the other side of the Big Bang, gravitational waves offer potential answer method. If characteristic signature of a bounce or pre-Big Bang phase exists in gravitational wave spectrum, detecting it would directly reveal that prior physics. We could observe gravitational echoes of the universe's origin, determining whether a bounce occurred, whether cycles exist, or whether smooth inflationary origin happened. This represents tangible path to answering our question through observation rather than pure theory. Though realizing this path requires major technological development, gravitational wave astronomy is in its infancy. Its maturation over coming decades might provide unexpected insights into cosmic origins. Particle physics experiments, though studying tiny scales, provide constraints on early universe models and thus indirectly on what might have preceded the Big Bang. Current limits suggest total neutrino mass is less than about 0.1 electron volts. Consistent with particle physics measurements, neutrinos decoupled from other matter very early, about 1 second after the Big Bang. A cosmic neutrino background should exist, though undetected so far. This background carries information about the universe at 1 second age, complementary to the CMB's 380,000-year snapshot. If pre-Big Bang physics affected neutrino properties or production, signatures might exist in the neutrino background. Dark matter, whose existence is inferred from gravitational effects, must have properties consistent with structure formation observations. The dark matter particle, whatever it is, must have been produced in early universe in right abundance to match observed density. Different dark matter candidates imply different early universe thermal histories. Supersymmetric particles, axions, and sterile neutrinos each have distinct production mechanisms. Whatever dark matter is, its properties constrain early universe temperature evolution, and thus models of the Big Bang and what preceded it. If dark matter was produced before a bounce, its properties would carry information through the bounce, potentially affecting our universe. The baryon asymmetry, the fact that matter dominates over antimatter, also constrains early universe physics. Somewhere in the first seconds, processes created slight excess of matter over antimatter. Most matter and antimatter annihilated, leaving the small excess. Explaining this asymmetry requires specific conditions in the early universe. Sakharov identified 3 necessary conditions for generating baryon asymmetry. These include baryon number violation, C and CP symmetry violation, and departure from thermal equilibrium. All must occur at some point. If a bounce preceded our expansion, baryon asymmetry might have been produced before, during, or after the bounce. The mechanism must work in bouncing cosmology. Some cyclic models face challenges explaining baryon asymmetry. If entropy increases each cycle, matter-antimatter balance might be restored, erasing asymmetry. Maintaining baryon asymmetry through cycles requires specific mechanisms that remain somewhat unclear. Grand unified theories suggest unification of forces at very high energies, around 10 to the 16th giga-electron volts. If gut transitions occurred in early universe, they might have produced magnetic monopoles, cosmic strings, or other exotic remnants. Observations find no monopoles, constraining gut physics and by extension inflation, which dilutes monopoles to undetectable densities. This constraint applies equally to pre-Big Bang scenarios. Whatever preceded must be compatible with non-observation of gut remnants. Supersymmetry, if it exists, suggests every particle has superpartner. None have been detected at LHC, pushing supersymmetry scale higher than many expected. This affects early universe models because supersymmetric particles would have been produced and affected evolution if SUSY scale is low enough. The absence of discovered SUSY particles so far suggests either SUSY is broken at higher scales or doesn't exist, affecting early universe predictions. String theory, which includes supersymmetry, faces constraints from particle physics non-discoveries. The theory must explain why SUSY is hidden if it exists. These particle physics constraints collectively provide boundary conditions on early universe scenarios. Whatever happened at or before the Big Bang must produce a universe evolving into the one we observe, with the particle content we measure. This is a strong requirement. Many speculative cosmological scenarios fail this test, predicting particle properties inconsistent with observations. Particle physics experiments continue pushing to higher energies and greater precision. Future colliders might reveal new particles or interactions. These discoveries would provide new constraints on cosmological models, further narrowing possibilities for pre-Big Bang physics. The interplay between particle physics and cosmology has become increasingly important. The early universe is laboratory for physics beyond accelerator reach. Conversely, particle discoveries constrain cosmological speculation, keeping it tethered to empirical reality. For understanding what's on the other side of the Big Bang, particle physics provides crucial consistency checks on theoretical proposals. Despite sophisticated observational techniques, fundamental limits exist on how directly we can probe what preceded the Big Bang. The cosmic microwave background provides our earliest electromagnetic view, from 380,000 years after the origin. Earlier than this, the universe was opaque to photons. No electromagnetic radiation from before recombination can reach us directly. This creates observational horizon in time. We cannot see earlier than recombination with photons, no matter how powerful our telescopes. Gravitational waves and neutrinos potentially probe earlier times because they interact so weakly with matter. The challenge is distinguishing genuine signatures from coincidences or effects explainable within our universe's evolution. This requires precise observations and careful statistical analysis. Claim detections must be robust against systematic errors and theoretical assumptions. The history of cosmology includes false alarms. The BICEP-2 B-mode detection turned out to be galactic dust. Other anomalies prove statistical flukes. Any claimed detection of pre-Big Bang signatures must survive. Similarly intense scrutiny before being accepted. The theoretical framework matters enormously for interpretation. Different theories predict different signatures from the same pre-Big Bang physics. Without correct theoretical framework, we might miss signatures or misinterpret them. Theory and observation must advance together. The fundamental challenge is that the further back we look, the more uncertain our theories become. General relativity works excellently for recent epochs. It becomes questionable near the Big Bang, where quantum effects matter. Quantum mechanics works excellently for laboratory scales. Its application to the entire universe's wave function remains conceptual challenge. Quantum gravity, necessary for describing the Planck epoch and before, doesn't exist as complete theory yet. Without quantum gravity, we're extrapolating beyond our theory's validity regime. Conclusions about pre-Big Bang physics are necessarily speculative. This doesn't mean the question is unanswerable, but that answers require breakthroughs in fundamental physics theory. Observation alone cannot tell us what preceded the Big Bang. We need both observations and correct theoretical framework to interpret them. progress requires parallel advances. Better observations constrain theories. Better theories suggest what observations might reveal. The interplay between theory and observation has driven cosmology's remarkable progress over the past century. The Big Bang model itself emerged from combining Hubble's observations of expansion with Einstein's general relativity. The CMB's discovery confirmed Big Bang predictions, providing crucial empirical support for the theoretical framework. Today we stand at a similar juncture. Observations are extraordinarily precise, but theoretical understanding of earliest moments remains incomplete. Breakthroughs in quantum gravity could enable interpreting existing observations in new ways, extracting information about pre-Big Bang physics. Or new observations might find unexpected phenomena that demand theoretical innovation to explain. The synergy between advancing theory and improving observations will likely determine how much we can learn about what preceded the Big Bang. But we must accept that complete certainty might never be achievable. Some aspects of ultimate origins might remain permanently beyond empirical verification. This is not failure, but honest acknowledgement of science's scope. Some questions might be answerable only to certain levels of confidence. Understanding what's on the other side of the Big Bang might ultimately rest on inference and plausibility rather than definitive proof. We can constrain possibilities, rule out inconsistent scenarios, favour probable ones, but absolute certainty might exceed what observation can provide. This is acceptable in science. Many important conclusions rest on strong evidence rather than absolute proof. The standard of evidence must be appropriate to the question. For cosmic origins, the standard is that proposed scenarios must be mathematically consistent, physically plausible, and compatible with all observations. Scenarios meeting these criteria remain viable. Those failing any criterion are rejected. This is how science progresses even when direct observation is impossible. The limits of observation are real but not paralyzing. Much can be learned within these limits through careful observation, rigorous theory, and thoughtful inference. The question of what's on the other side of the Big Bang connects deeply to philosophical questions about causation and what constitutes adequate explanation. In everyday experience, every event has a cause. Things don't just happen spontaneously. Something makes them happen. This causal principle seems fundamental to understanding the world. Science seeks causes for phenomena, building causal chains explaining effects. But does the universe as a whole require a cause? Can we ask what caused the Big Bang, or is this question somehow inappropriate? If time began at the Big Bang, then cause becomes problematic. Causation requires temporal ordering. Causes precede effects in time. If there's no time before the Big Bang, there's no temporal slot for a cause to occupy. The concept of cause might not apply. This would make the Big Bang self-explanatory in a sense. It doesn't need external cause because causation requires time that doesn't exist beforehand. But this seems to dodge rather than answer the question. We want to know why the universe exists, why the Big Bang happened. This makes the universe like a mathematical truth, existing necessarily rather than contingently. But necessity is usually reserved for abstract entities like mathematical objects or logical truths. Can a physical universe exist necessarily? Some argue that if existence follows from mathematical consistency, and the universe is a mathematical structure, then existence is necessary. The mathematical universe hypothesis suggests all mathematically consistent structures exist necessarily. Our universe is one such structure. This makes existence necessary and self-explanatory. The universe doesn't need external cause because existence is automatic for consistent mathematics. Critics question whether mathematics can ground physical existence. Isn't mathematics abstract, requiring concrete instantiation? The debate between mathematical Platonism and nominalism becomes relevant. Do mathematical objects exist independently of physical reality? These are deep philosophical questions without consensus answers, unlikely to be resolved by science alone. Another perspective comes from considering the universe as a closed causal loop. Later states might cause earlier states through backward causation. This is permitted in some interpretations of general relativity, where closed time-like curves can exist. If causation can loop back, the universe might be self-causing without needing external initial cause. But backward causation is deeply problematic, threatening paradoxes like the grandfather paradox. Most physicists reject it or treat it as unphysical. The question of causation for the Big Bang might be uniquely challenging because it sits at the boundary of physics. Physical laws describe relationships between states in time. At the universe's origin, these relationships might break down or require reformulation. Perhaps causation itself is emergent, applicable within space-time but not to space-time's origin. This would make asking for the Big Bang's cause a category error, applying concept beyond its domain of validity. Or perhaps multiple types of explanation exist. Scientific explanation through physical laws is one type. Mathematical necessity is another. Metaphysical explanation yet another. The Big Bang might require metaphysical explanation that science alone cannot provide, though it can constrain what metaphysical explanations are plausible. For understanding what's on the other side of the Big Bang, the causation question matters because it frames what kind of answer we seek. If we want causal explanation, we need prior state causing the Big Bang. If we accept a causal quantum origins, no prior state is necessary. If we demand sufficient reason, we need some principle explaining the universe's existence, whether internal necessity or external cause. Different philosophical frameworks lead to different acceptable answers. Science constrains but doesn't uniquely determine which framework is correct. This is why the question remains partly philosophical, even as science makes progress. The empirical and conceptual aspects intertwine. Understanding this interplay helps clarify what progress is possible and what questions might remain even with complete physical theory of cosmic origins. Whether the universe exists necessarily or contingently profoundly affects how we think about what, if anything, preceded the Big Bang. Something necessary exists in all possible worlds. It couldn't fail to exist. Its existence follows from its nature rather than being contingent on circumstances. Mathematical truths are paradigm examples of necessary truths. 2 + 2 = 4 in all possible worlds. The Pythagorean theorem is necessarily true. Something contingent exists in some possible worlds but not others. Its existence depends on circumstances that might have been different. Most physical objects are contingent. This particular chair exists. But circumstances could have been different such that it didn't exist. Is the universe necessary or contingent? This is one of philosophy's deepest questions with profound implications. If the universe exists necessarily, then asking what preceded the Big Bang might be asking for explanation of something that had to happen. The multiverse perspective affects the question. If infinitely many universes exist, our universe's particular properties are contingent, selected from vast possibilities. But the multiverse itself might exist necessarily if it's the structure mathematical consistency requires. This makes the collection of all universes necessary, while individual universes remain contingent, combining both elements. The mathematical universe hypothesis explicitly claims existence is necessary. All mathematically consistent structures exist because consistency implies existence. Non-existence would itself be a mathematical structure. So it cannot be the case that nothing exists. Something must exist necessarily. This makes the universe necessarily existent at the level of mathematical structure. Though our particular universe might be one among many, critics question whether mathematical consistency genuinely implies physical existence. This seems to confuse abstract with concrete, but proponents argue the distinction between mathematical and physical breaks down at the fundamental level. Mathematics is all there is. If this is true, existence is necessary, and the question of what preceded the Big Bang becomes a question about mathematical structure. What's on the other side might be another region of mathematical structure space. necessarily existing like our universe but with different properties. The problem of contingency also relates to fine-tuning. The universe's physical constants appear finely tuned for life to exist. If constants were slightly different, stars, planets, and life couldn't exist. This seems too fortunate to be coincidental if the universe is contingent. Some see this as evidence for necessity. Perhaps the constants are determined by deeper principles that require their specific values, or perhaps the multiverse explains fine-tuning anthropically. In vast ensemble, some universes have life-compatible constants by chance, or perhaps intentional design explains fine-tuning. A necessary being chose constants to permit life, making our universe's properties contingent on that choice. These options represent different philosophical frameworks for understanding existence: necessity through mathematical or physical principles, contingency through multiverse and anthropic selection, or contingency through intentional creation. Each framework suggests different answers to what preceded the Big Bang. Necessary existence suggests the Big Bang had to occur for logical or physical reasons. Contingent existence suggests the Big Bang might not have occurred, requiring explanation of why it did. Perhaps through prior state or quantum probability. Current physics cannot definitively determine whether the universe is necessary or contingent. The question requires metaphysical reasoning beyond empirical science. But physics constrains possible answers. Whatever metaphysical framework we adopt must be compatible with observed physical laws and cosmic properties. For instance, if the laws of physics could have been different, as the landscape of string theory suggests, then our particular laws are contingent. But if only one mathematically consistent set of laws is possible, as some unified theories might imply, then the laws are necessary. These are open questions at the intersection of physics and philosophy, unlikely to be resolved soon. Understanding the necessity versus contingency question helps frame what kind of explanation we seek for what preceded the Big Bang. If necessary, we seek logical or mathematical principles. If contingent, we seek causes or probabilistic mechanisms. The answer affects not just cosmology, but philosophy of science, metaphysics, and theology. It touches fundamental questions about reality's nature. The question of what preceded the Big Bang inevitably leads to contemplating nothing, perhaps the most perplexing concept in philosophy. If time began at the Big Bang, what existed before? The tempting answer is nothing. But what does nothing mean? In everyday language, nothing means absence of things. An empty box contains nothing, meaning no objects, though it contains air and space. But absolute nothing would mean no objects, no space, no time, no energy, no laws, no mathematics, no possibilities. Complete and total absence. Can absolute nothing exist? Or is existence somehow necessary, making true nothing impossible? If absolute nothing could exist, why does something exist instead? Why is there a universe rather than nothing at all? Perhaps nothing is quantum mechanically impossible. Any state we might call nothing contains quantum fields and vacuum energy. This quantum nothing is still something. It has structure, obeys laws, contains energy. It's not absolute nothing. Could absolute nothing be the quantum ground state? The lowest energy configuration of all fields with no particles present? Even this isn't absolute nothing, because fields themselves exist along with the laws governing them. To reach true nothing, we'd need to remove not just particles and fields, but space-time itself, physical laws, quantum mechanics, mathematics. This seems incoherent. How can we even conceive of such total absence? Our thoughts presume logical structure that absolute nothing would lack. Some philosophers argue absolute nothing is logically impossible. The concept contradicts itself by being a concept. To think about nothing is to make it something. An object of thought. True nothing would be unthinkable, inconceivable. If nothing is impossible, then something exists necessarily. Existence is fundamental, and the question of why something rather than nothing dissolves. There never was an option of nothing. Existence in some form was always inevitable. This makes the universe's existence less surprising. It exists because existence itself is necessary, though the particular form might be contingent. What's on the other side of the Big Bang in this view cannot be nothing because nothing is impossible. It must be something, quantum state, previous universe, mathematical structure, or something we haven't conceived. The Big Bang might be transition from one form of existence to another, not from nothing to something. Lawrence Krauss argued that physics explains how a universe can come from nothing, defining nothing as empty space with quantum fields. Critics objected this isn't true nothing. Quantum fields and space are something. The problem of absolute nothing remains. Krauss responded that true nothing is incoherent concept. The physically meaningful nothing is quantum vacuum, and universes can arise from this. If quantum vacuum, then physics potentially explains it. If absolute nothing, then explanations might need to be metaphysical or theological. If nothing is impossible, then the Big Bang emerged from something. And the question becomes, what was that something? Understanding the problem of nothing clarifies what we're asking when we inquire about what preceded the Big Bang and what kind of answer would satisfy. The question of what preceded the Big Bang requires understanding time's nature, which might be stranger than everyday experience suggests. We experience time as flowing steadily forward, dividing reality into past, present and future with sharp boundaries. But physics treats time differently. In relativity, time is relative, different for different observers. No absolute simultaneity exists. This already contradicts intuition. Events that are simultaneous for one observer occur at different times for another, moving differently. Perhaps at fundamental level, reality is timeless. Time emerges only in certain regimes or approximations, not present in deepest description. This would make temporal questions about origin somewhat misguided. We're applying emergent concept to a situation where it doesn't yet apply. Loop quantum gravity also suggests time might be emergent from quantum geometric structures. Spin networks don't evolve in time, but simply are. Time appears when we consider semi-classical approximations, where large-scale behaviour can be described in temporal terms. If time is emergent, what does this mean for causation and explanation? Are these also emergent concepts valid only approximately? Perhaps at the deepest level, reality is a timeless quantum state or mathematical structure. Temporal descriptions are useful approximations for certain purposes. The Big Bang would then be a feature of emergent temporal description, not a moment in fundamental timeless reality. What's on the other side wouldn't make sense in temporal terms. The question would need reformulation in terms of fundamental timeless structure. This is philosophically radical. Time seems so fundamental to experience that imagining reality without it is nearly impossible. Yet physics hints that time might not be as fundamental as it seems. Space and time emerge from quantum foam. Perhaps time itself emerges from something deeper. Another perspective comes from considering time's arrow. Time seems to have direction. Forward toward future, not backward toward past. This arrow is related to entropy increase, the second law of thermodynamics. Entropy increases toward future, giving time direction. But microscopic physical laws are time-symmetric. Reverse any process and it obeys the same laws. Time symmetry is fundamental. How can fundamental time symmetry give rise to experienced time asymmetry? This is the arrow of time problem. The answer likely involves special low-entropy initial conditions at the Big Bang. The universe started in very low-entropy state. As it evolved, entropy increased toward equilibrium, creating thermodynamic arrow pointing away from Big Bang toward future. But this pushes the question back. Why were initial conditions low entropy? This seems like special fine-tuned condition requiring explanation. If something preceded the Big Bang, did it also have time arrow? If cyclic, how is entropy reset to allow next cycle? These questions about time's arrow connect to questions about what preceded the Big Bang and whether temporal descriptions even apply. Understanding time's nature is thus crucial for understanding cosmic origins. If time is fundamental, the question of what came before makes sense. If time is emergent, the question needs reformulation. We're asking about structure underlying emergent time, not about temporal precedents. Current physics doesn't definitively answer whether time is fundamental or emergent. Different quantum gravity approaches make different assumptions. String theory often treats time conventionally, as a parameter describing evolution. Loop quantum gravity explores timeless formulations. The correct answer awaits complete quantum gravity theory that can be tested against observations, for our questioned. The implication is that what preceded the Big Bang might not be a prior time but a different aspect of timeless fundamental reality. Or time might extend through the Big Bang, connecting our universe to previous phase in genuinely temporal sequence. The answer depends on time's true nature, which remains one of physics' deepest unresolved questions. The anthropic principle provides one lens for thinking about what preceded the Big Bang. Especially in multiverse contexts, the weak anthropic principle is almost tautological. We observe conditions compatible with our existence, because incompatible conditions wouldn't have observers. This explains why we find ourselves in a habitable universe without requiring the universe to be typical or special. If a multiverse contains many universes with varying properties, we necessarily observe one where our type of life can exist. The strong anthropic principle makes bolder claim. The universe must have properties allowing observers because observation is somehow necessary. High-entropy universes are featureless equilibrium states where nothing interesting happens and no observers evolve. If multiverse produces both low and high-entropy beginnings, we necessarily observe low-entropy beginning anthropically. The Big Bang's specific properties might be anthropically selected from range of possibilities in eternal inflation or quantum cosmology. We observe this particular Big Bang because its properties led to a universe where life and observers could develop. This doesn't explain why any universe has life-compatible properties, only why our universe does if many exist. Critics argue anthropic reasoning is unscientific because it doesn't make testable predictions. We observe what we observe. Anthropics adds no information. Proponents counter that anthropic reasoning makes statistical predictions. Our universe should be typical among life-permitting universes. If we observe properties extremely atypical among life-permitting possibilities, it would challenge anthropic explanation. This requires understanding the distribution of properties across multiverse, which is difficult without complete theory. String theory's landscape potentially provides such distribution. Different vacua have different probabilities and properties. If most life-permitting vacua have certain properties, and we observe different properties, anthropic explanation becomes questionable. So far, analyses suggest our universe's properties are roughly what anthropic reasoning predicts, neither extremely typical nor atypical. But these analyses are preliminary given uncertainties in string landscape and anthropic criteria. The anthropic perspective also affects how we think about uniqueness. If multiverse exists, our universe isn't unique. Infinite bubbles with our properties exist elsewhere. We're one among infinitely many similar universes. This can seem to diminish cosmic significance. If infinite copies exist, why does our particular universe matter? But significance comes from our subjective experience, not from uniqueness. Each universe matters to its inhabitants. What preceded our Big Bang, in multiverse context, is structure generating all universes, ours being one anthropically selected example. The mechanism generating universes, eternal inflation or quantum cosmology, is the fundamental structure. Individual Big Bangs are phenomena within it. Understanding what preceded our Big Bang then means understanding eternal inflation or quantum cosmology, not finding prior universe in temporal sequence. The anthropic perspective thus reframes the question, is not asking what came before, but what selection mechanism explains our properties. This is a different type of explanation, teleological in flavour though not requiring purpose or design. We explain our universe's properties by pointing to observer requirements rather than detailed causal history. Whether this satisfies depends on philosophical temperament. Some find anthropic reasoning explanatory, others find it evasive or circular. For our exploration, the anthropic perspective represents one way of thinking about cosmic origins that doesn't require detailed knowledge of pre-Big Bang physics. Even with uncertainty about what preceded the Big Bang, we can explain why we observe this particular universe if many exist. The anthropic perspective is thus complementary to physical theories. It explains why we observe what we do given physical multiverse structure. But it doesn't replace need for physical understanding of that structure. We still want to know how multiverse works and whether it exists. Anthropic reasoning is tool for interpreting observations and understanding our place, not substitute for fundamental physics. After exploring theoretical possibilities and observational constraints, it's worth assessing what we can realistically know about what preceded the Big Bang. Direct observation of pre-Big Bang physics is likely impossible. Any information from that era comes filtered through subsequent evolution. The Planck epoch at 10 to the minus 43 seconds represents barrier to direct observation. Earlier physics is hidden behind this barrier. The first 3 minutes, during Big Bang nuclear synthesis, are well understood. Predictions match observed light element abundances precisely. Going earlier, into the first second when neutrinos decoupled, theory remains solid though direct observations are limited. Before 1 second into the realm of particle physics beyond standard model, uncertainty grows, but frameworks like inflation provide successful descriptions. Inflation itself is strongly supported indirectly through its predictions about flatness, homogeneity, and fluctuation spectrum. But inflation's specific mechanism, the inflaton field's properties, remain uncertain. Many inflation models exist. Observations don't yet distinguish them. What preceded inflation, or how inflation began, is even more uncertain. Here we enter a realm of quantum cosmology and quantum gravity. Bounces, brains, quantum tunneling, no boundary proposals all remain speculative. None have definitive observational support or theoretical proof. They're serious scientific ideas explored by leading researchers, but they're hypotheses rather than established facts. The honest assessment is that we don't know what preceded the Big Bang with any certainty. We have plausible ideas but not definitive knowledge. This isn't failure, it's frontier of knowledge. Not knowing is impetus for continued research, driving theoretical and observational advances. What can we know in principle? This depends on whether information from pre-Big Bang era can survive into our observable universe. If bounces or transitions erase all information from prior state, the past becomes fundamentally unknowable. If some information transfers through, perhaps in fluctuation patterns or geometric properties, then observation could eventually reveal it. Determining which is correct requires understanding quantum gravity's behaviour at extreme conditions, which we don't yet have. We might eventually develop quantum gravity theory allowing definitive predictions about what happens at singularities and bounces. These predictions could be tested against CMB observations, gravitational wave backgrounds, or other data. If theory and observation align, confidence in pre-Big Bang scenarios would grow, even without direct observation of prior universe. This is acceptable. Science doesn't require certainty, only evidence-based conclusions with appropriate confidence levels. For understanding what preceded the Big Bang, we might achieve high confidence in general framework, bounce or quantum origin, while details remain uncertain. Or we might narrow to a few scenarios unable to definitively choose between them observationally. Either outcome represents significant progress from current state, where many scenarios remain viable. The key is maintaining scientific rigour. Speculation must be constrained by consistency with known physics and observations. Wild speculation untethered to evidence doesn't advance understanding. Careful exploration of plausible scenarios consistent with constraints does. What we can know is bounded by observational limits and theoretical uncertainty. But within these bounds, meaningful progress is possible. The question of what preceded the Big Bang might never be answered with absolute certainty, but it can be addressed scientifically, narrowing possibilities through evidence and reasoning. This is how science works at its frontiers. Not with definitive answers, but with increasingly constrained and probable scenarios. Understanding this helps set realistic expectations. We seek understanding, not certainty. We build models, not absolute truth. The journey of inquiry is valuable even if final destination remains partially obscured. Each step forward increases understanding. One striking feature of current understanding is that multiple plausible answers exist to what preceded the Big Bang, each with different strengths. Rather than finding this frustrating, we might appreciate the richness of possibilities as reflecting the question's depth and our understanding's current state. Loop quantum cosmology offers concrete mathematical framework, predicting quantum bounce connecting to previous contracting universe. This has appeal of being calculable and making testable predictions. It extends physics through singularity using quantum gravity principles. This pluralism is common in frontier science. When exploring unknown territory, multiple paths must be tried before determining which leads forward. Historically, physics has resolved similar situations through theoretical breakthroughs or observational discoveries that favour one approach decisively. Perhaps future quantum gravity theory will clearly favour one scenario, showing it follows naturally from correct principles. Or future observations might detect signatures that discriminate between scenarios, empirically determining which describes reality. Until then, maintaining multiple scenarios allows exploring different possibilities without prematurely committing to one. This openness is scientifically healthy. Dogmatically insisting on one answer without sufficient evidence impedes progress. Different scenarios also probe different aspects of reality's structure. Each teaches us something even if not ultimately correct. Loop quantum cosmology reveals insights about quantum geometry. String theory explores higher dimensions and dualities. Hartle-Hawking teaches about quantum cosmology. Vilenkin explores quantum origins. Cyclic models examine eternal time evolution. Each contribution is valuable for developing understanding. Even if only one eventually proves correct or none prove exactly right. The scenarios also fulfill different explanatory needs. Some seek mathematical inevitability, others seek causal mechanism, still others seek philosophical coherence. These different needs reflect different questions we're asking. What's on the other side of the Big Bang in mathematical terms? What physically caused the Big Bang? Why does anything exist? What's the ultimate ground of reality? These are related but distinct questions. Different scenarios address different ones most directly. Perhaps no single scenario addresses all questions fully. Perhaps complete understanding requires synthesizing insights from multiple approaches. The future theory might incorporate bounce mechanisms from loop quantum gravity, multiverse structure from inflation, mathematical framework from string theory. Such synthesis would draw on strengths of each approach while avoiding individual weaknesses. Or the correct answer might be entirely different from all current scenarios, something we haven't yet imagined. History shows that revolutionary insights often come from unexpected directions, overthrowing assumptions that seemed secure. We should remain open to possibilities beyond current frameworks while rigorously exploring frameworks we have. The appeal of multiple answers is that they keep us intellectually honest, preventing premature closure before evidence warrants it. They also keep research community productive. Different groups pursue different approaches, increasing chances someone will find the right path. If everyone pursued the same approach and it proved wrong, decades could be wasted. Diversity of approaches is insurance against this. From an educational perspective, multiple scenarios help convey the frontier's genuine uncertainty, while maintaining scientific rigour. Students learning cosmology should understand that some questions remain open, with scientists actively debating alternatives. This provides a realistic picture of how science works, not as a collection of settled facts, but as ongoing inquiry into nature's mysteries. It also inspires, showing that fundamental questions remain where breakthrough contributions are possible. For the general public, multiple scenarios might seem confusing. Why can't scientists agree on what preceded the Big Bang? But honest communication includes admitting uncertainty. We don't yet know is valid and important scientific statement. It shows science's intellectual integrity, willingness to acknowledge limits rather than pretending to knowledge it doesn't have. The appeal of multiple answers ultimately is that they reflect reality of frontier research where understanding is incomplete but progress continues. They show question is being taken seriously, explored rigorously from multiple angles, gradually converging toward eventual answer. Mathematics plays central but puzzling role in understanding what might have preceded the Big Bang, raising questions about math's relationship to physical reality. Physical theories are expressed mathematically. General relativity describes space-time geometry. Quantum mechanics uses Hilbert spaces and operators. This mathematical description is extraordinarily successful. Equations predict observations with remarkable precision across vast domains. But why does mathematics describe reality so well? Is it merely human tool, or does it reveal something fundamental about reality's nature? Eugene Wigner's essay on mathematics' unreasonable effectiveness in physics highlights this mystery. Why should abstract mathematical structures correspond to physical reality? One answer is that mathematics is the language of nature. Physical law is inherently mathematical, and we're discovering rather than inventing this structure. This Platonist view treats mathematical objects as real, existing independently of minds. Physical reality instantiates or embodies mathematical structures. If this is correct, understanding what preceded the Big Bang requires understanding mathematical structures describing cosmic origins. The universe's beginning is encoded in equations of quantum cosmology. Solving those equations reveals what happened and what preceded it. Mathematics determines possibilities and necessities. What's mathematically impossible cannot be physical. What's mathematically necessary might be physically inevitable. This gives mathematics explanatory power. The universe behaves as it does because mathematical structures constrain what's possible. The mathematical universe hypothesis takes this further, identifying physical with mathematical. All consistent mathematical structures are equally real universes. Our universe is one such structure. What preceded our Big Bang is a question about mathematical structures' properties, not about causes in time. This makes mathematics not just descriptive but fundamental to existence itself. Reality is mathematics, and physics discovers which mathematics describes our experience. Alternative view treats mathematics as human creation, useful for modelling reality but not identical to it. Mathematics is abstract formal system invented by minds. Its effectiveness is partly accident, partly a result of selecting mathematics that works. Many mathematical structures find no application in physics. We notice the few that work and forget the rest. Creating impression mathematics is uncannily effective. In this nominalist view, what preceded the Big Bang is physical question not reducible to mathematical one. Mathematics helps us describe it but isn't the explanation. These philosophical positions dramatically affect how we think about cosmic origins and what constitutes explanation. For Platonists, mathematical inevitability explains physical existence. The universe exists because its mathematical structure is consistent. For nominalists, mathematics describes but doesn't explain. Physical causes or quantum probabilities explain existence, with mathematics being our description language. Practically, physicists use mathematics without resolving these philosophical questions. But the questions become relevant at cosmic origins. If time began at Big Bang, mathematical description might be all there is. There are no physical causes in time, only mathematical structures. The wave function of the universe satisfying Wheeler-DeWitt equation might be complete description. What preceded the Big Bang is whatever mathematics specifies, or mathematics might be provisional description of underlying reality transcending mathematical formalism. Reality is richer than any mathematics can capture. These possibilities can't be resolved by physics alone. They require philosophical reflection on mathematics' nature and relationship to reality. But physics constrains philosophy. Whatever view we adopt must account for mathematics' extraordinary success in physics. The precision with which mathematical theories predict observations suggests mathematics touches reality's essence, even if not identical to it. For quantum cosmology specifically, mathematics is indispensable. The wave function is mathematical object. Hilbert's spaces and operators are mathematical structures. Asking what preceded the Big Bang requires manipulating these mathematical structures according to quantum theory's rules. The answers we get are mathematical: probability amplitudes, wave function solutions, expectation values. These mathematics correspond to physical predictions. The amplitude for universe tunneling from nothing is both mathematical object and physical probability. The distinction between mathematics and physics blurs at this level. Calculating equals predicting. Mathematical properties determine physical outcomes. This intimate connection suggests that understanding cosmic origins requires deeper understanding of mathematics itself and its relationship to existence. String theory embodies this connection. The theory is fundamentally mathematical, emerging from consistency requirements in quantum field theory. Many string theory developments came from pure mathematics: Calabi-Yau manifolds, mirror symmetry, moduli spaces. Yet these mathematical structures allegedly describe physical reality, suggesting deep unity between mathematical consistency and physical possibility. If string theory is correct, what preceded the Big Bang is question about string theory's mathematical structure, higher dimensions, and brain dynamics. The answer is inherently mathematical even while being about physical reality. The two can't be separated. This might ultimately vindicate Platonism. At physics foundations, mathematical and physical become indistinguishable. Or it might show mathematics is so useful that we've structured our theories to be mathematical, even when underlying reality isn't purely mathematical. Resolving this requires completing quantum gravity and understanding whether unique mathematical structure emerges or multiple equally consistent structures exist. If unique structure, it might suggest mathematical inevitability. If multiple structures, it suggests mathematics is a flexible tool rather than reality's essence. For now, mathematics remains indispensable for exploring what preceded the Big Bang. All serious proposals are mathematical theories. Whether mathematics is tool, description, or reality itself, working with mathematics is how we make progress on these deepest questions. Understanding the role of mathematics helps appreciate why progress is difficult. We're pushing mathematics to describe something that might transcend mathematics, or we're discovering mathematics is all there ever was, with physical intuition merely guiding us through mathematical landscape of possibilities. Either way, mathematics bridges our limited experience and ultimate cosmic questions about origins and existence. Understanding what preceded the Big Bang might seem abstract and distant from human concerns, yet it connects to profound questions about meaning and significance. The answer affects worldview, how we understand our cosmic context and existence's nature. If time began at Big Bang, we're part of finite cosmic story with definite beginning, possibly heading toward definite end. This creates narrative structure with temporal boundaries, giving cosmic history shape and direction. If time extends infinitely through bounces or cycles, we're part of eternal story without beginning or end, just endless transformation. This challenges notions of ultimate origins and suggests existence has no first cause, simply eternal being. If multiverse exists with our universe one among many, cosmic significance changes. We're not in the universe but a universe. Our cosmic importance diminishes in one sense but persists in another. Our universe matters to us even if countless others exist. These different scenarios affect meaning in subtle ways. Meaning comes primarily from our lives and relationships, not cosmic context. But cosmic understanding provides backdrop influencing how we think about ourselves and our place in larger reality. Knowing we're part of eternal cyclic process might inspire different attitudes than knowing we're in unique finite universe. Knowing infinite universes exist might affect how we value our particular existence and circumstances. These effects are psychological and philosophical rather than logical. Cosmic context doesn't determine meaning, but it colours our perspective. Religious and spiritual traditions have long connected cosmology to meaning and purpose. Different cosmic stories support different theological frameworks. Finite beginning at Big Bang is compatible with creation theology. Eternal cycles resonate with certain Eastern philosophies. Multiverse scenarios challenge uniqueness, but might support theological ideas about infinite creation or divine exploration of possibilities. Scientific cosmology doesn't prove or disprove religious interpretations, but constrains what interpretations are plausible given physical evidence. For secular perspectives, cosmic origins affect philosophical questions about existence, causation, and necessity without invoking supernatural. Why does anything exist becomes central philosophical question if universe could have not existed? If universe exists necessarily through mathematical or physical principles, it provides naturalistic answer without requiring external explanation. Different answers to what preceded the Big Bang suggest different ontological frameworks, affecting how we think about reality's fundamental nature. The question also inspires wonder and intellectual humility. The fact that we can ask about origins and develop theoretical frameworks is remarkable. Yet the answer remains uncertain despite sophisticated physics and observations. Some mysteries persist even as understanding advances. This combination of capability and limitation defines human condition. We can comprehend vastly more than our direct experience, yet ultimate questions remain. Appreciating this balance promotes intellectual humility while maintaining curiosity and wonder. Cosmological understanding also provides perspective on human concerns. Our worries and struggles occur against backdrop of cosmic evolution. This perspective doesn't diminish personal significance but contextualizes it within larger reality. Understanding that everything we see emerged from Big Bang 13.8 billion years ago, and possibly from something even before that, invites reflection on time's passage. Human civilization is briefly recent. Recorded history spans mere thousands of years. The cosmic story spans billions. Yet within our brief moment we've developed understanding reaching back to cosmic origins. This intellectual achievement is itself significant. It demonstrates consciousness's remarkable capacity to reflect on its own existence and origins, arguably one of universe's most interesting features. Whether this capacity is common throughout universe or rare affects how we value it. If consciousness is ubiquitous, our perspective is shared widely. If rare, our understanding of cosmic origins is precious, one of few locations where universe contemplates itself. The anthropic principle suggests we're not typical observers if typical means most common. We might be rare or even unique. But we're typical in the sense that we observe universe compatible with our existence, which provides all we can observe. This affects how we interpret our cosmic situation. We're necessarily in special circumstances, but special doesn't mean unique or purposeful. For meaning and purpose, cosmic origins provide context but don't determine values. We create meaning through choices and relationships, but understanding context enriches this meaning-making. Knowing we're part of cosmic story, whether finite or infinite, connects personal to universal. The question of what preceded Big Bang is thus not merely technical, but touches human concerns about origins, meaning, and place in reality. Different answers suggest different worldviews, though they don't logically require any particular philosophy or theology. The openness of the question, with multiple plausible answers, allows different people to find different meanings compatible with physical evidence. This pluralism is valuable. Science constrains but doesn't fully determine worldview, leaving space for philosophical and spiritual interpretation. Understanding what we know and don't know about cosmic origins helps integrate scientific knowledge with broader human concerns. It shows how frontier science connects to timeless questions about existence and meaning that humans have always contemplated. The significance for humanity is partly in the knowledge itself, partly in the intellectual journey of seeking answers, and partly in recognizing that some mysteries may forever exceed complete understanding while remaining accessible to thoughtful inquiry. As we conclude our exploration, perhaps the most important insight is learning to embrace mystery rather than fear or fight it. The question of what's on the other side of the Big Bang might never be answered with certainty. This isn't failure, but reflects reality's depth. Some questions resist complete resolution not from ignorance, but from fundamental constraints on knowledge, observation, and perhaps conceptualization itself. The Planck epoch represents barrier to direct observation. Whatever happened, there cannot be seen, only inferred. Even with perfect quantum gravity theory, applying it to unique event of universe's origin involves uncertainties that might not be eliminable. The universe's beginning is singular in all senses, unique, extreme, and potentially beyond complete comprehension. Accepting this doesn't mean abandoning inquiry. We continue exploring, developing theories, making observations, narrowing possibilities, but we acknowledge that perfect knowledge might be impossible, and this is acceptable. Mystery isn't gap to be filled with knowledge, but feature of reality deserving appreciation and respect. The fact that universe has origins we can contemplate but not fully fathom adds depth and wonder to existence. If everything were known, if all questions had definitive answers, reality might seem less profound, more mechanical. Mystery preserves sense of reality transcending human understanding, while remaining partially accessible to thoughtful investigation. This balance seems optimal for maintaining both scientific progress and sense of cosmic wonder. The history of science shows many mysteries have been resolved through persistent investigation. Unknowns become knowns routinely. But some mysteries might be permanent, built into reality's structure rather than artifacts of current ignorance. Whether Big Bang's origin is temporary or permanent mystery remains to be seen. Future might bring clarity, or might confirm fundamental uncertainty. Either way, the question is worth asking. The inquiry itself advances understanding, even without reaching final answers. We've learned about quantum gravity's role, about possible bounces and cycles, about emergence of time and space from quantum substrate. These insights are valuable regardless of whether they definitively answer what preceded the Big Bang. They deepen understanding of matter, energy, space, and time at extremes. They connect to fundamental questions in physics and philosophy. The journey of exploration creates intellectual progress and human meaning, independent of reaching final destination. Embracing mystery means appreciating this process-oriented view of inquiry. Knowledge-seeking is valuable in itself, not just for conclusions reached. It also means accepting limits with grace. We're finite beings in vast reality. Complete omniscience is neither achievable nor necessary. Partial understanding is still understanding. Probable answers are still answers. Constrained possibilities are better than unconstrained speculation. Science progresses by narrowing possibilities, increasing confidence in some scenarios while eliminating others. This incremental progress might not satisfy desire for definitive revelation, but it's how understanding actually advances. For what preceded the Big Bang, we've narrowed from infinite possibilities to a handful of plausible scenarios. Future work will likely narrow further, increasing confidence in one or eliminating some as incompatible with observations. Eventually, one scenario might become overwhelmingly probable, even without direct observation of pre-Big Bang physics, or multiple scenarios might remain viable, distinguished only by unobservable details or philosophical preferences. Either outcome represents success, understanding advanced, questions clarified, possibilities constrained by evidence and reasoning. The mystery isn't defeated, but is engaged with rigorously, scientifically, honestly. This honest engagement includes acknowledging what we don't know, what we can't know, and what we might never know. It includes recognizing that some answers are inherently uncertain, resting on inference rather than direct observation. It includes accepting that physical theories have limits, beyond which metaphysical or philosophical reasoning must complement scientific investigation. These acknowledgements don't weaken science, but strengthen it by maintaining intellectual honesty about its scope and methods. Science is extraordinarily powerful for answering certain types of questions about natural phenomena, but it might not answer all questions, particularly those about ultimate origins involving unique, unrepeatable events at limits of observation. This doesn't make the questions meaningless or unanswerable, only that answers require more than science alone. Philosophy, mathematics, perhaps even theology, contribute insights to questions at reality's boundaries. Embracing mystery means accepting this pluralism of approaches while maintaining scientific rigor for empirical aspects. It means staying curious, continuing to explore, while finding peace with uncertainty and incompleteness. The question of what's on the other side of the Big Bang encapsulates this attitude perfectly. We can investigate it scientifically, develop theories, make observations, constrain possibilities. But we might never achieve certainty, and that's acceptable. The question's depth exceeds our complete comprehension. We explore as far as possible, appreciate what we learn, and accept what remains beyond reach. This embrace of mystery is mature scientific and philosophical stance, neither arrogantly claiming complete knowledge nor desperately demanding it. It's balance between ambitious inquiry and humble acceptance, between pushing boundaries and recognizing them. For understanding what preceded the Big Bang, this balance is essential. We reach for understanding while acknowledging mystery's permanence. We use science, mathematics, philosophy, and reason to probe as deeply as possible, and we appreciate the wonder of existence itself, the fact that anything exists and that we can contemplate its origins. This appreciation deepens rather than diminishes through inquiry. Understanding enhances wonder rather than eliminating it. What's on the other side of the Big Bang? We've explored possibilities, bounces, quantum origins, emergent time, multiverse structure. Each possibility is fascinating, revealing different aspects of reality's potential structure. The definitive answer eludes us still, and might always. But the exploration enriches understanding and experience. This is human beings at our best, curious, thoughtful, humble, and persistently seeking understanding of the deepest questions. The mystery invites continued inquiry, while inspiring awe at reality's profound depths. Thank you for journeying with me through this exploration of what might lie on the other side of the Big Bang, this patient investigation of origins and beginnings. I hope you found peace in recognizing that some questions remain beautifully open, that uncertainty enriches rather than diminishes understanding, and that mystery is a feature of reality deserving appreciation. What's on the other side of the Big Bang? We've explored quantum bounces connecting to previous universes, smooth timeless origins without temporal before, universes tunneling from quantum nothing, eternal inflation spawning infinite bubbles, emergent time from timeless structures. Each possibility is scientifically serious, philosophically rich, and yet uncertain. Wherever you are now, I hope you're ready for deep rest. Your breathing has found its gentle rhythm. Your mind has released its need for definitive answers to impossible questions. The mysteries we've explored perhaps help you feel both small in cosmic vastness and significant in your capacity to contemplate existence's origins. Sleep well tonight, knowing you're part of a universe that emerged from something, possibly from nothing, possibly from something we cannot yet imagine. Whether time began 13.8 billion years ago or extends eternally through cycles, whether our universe is alone or one among infinite others, you exist here now to contemplate these questions. Dream peacefully of quantum fluctuations creating universes, of time emerging from timelessness, of bounces connecting cosmic epochs. Dream of mathematics giving birth to reality, of existence being necessary rather than contingent. Dream of mysteries that inspire rather than frustrate, of questions whose depth exceeds their answers. Good night. May your sleep be undisturbed and restorative. May tomorrow find you refreshed and renewed. And may you carry forward an appreciation for profound questions, comfort with uncertainty, and wonder at reality's origins that we can explore but might never fully comprehend. What's on the other side of the Big Bang? Quantum possibilities, previous universes, timeless structures, or perhaps nothing at all? We don't know with certainty. Perhaps we can't know. Perhaps the question needs reformulation, but exploring it reveals universe's depths and humanity's remarkable capacity to contemplate existence itself. Good night.